Hello and welcome to Fractal, my planet generation project where I aim to make fully destructible planets. As I finally felt that the channel was lacking any dev content, I decided to make this short video on the most recent project I've been working on, and I thought I'd show it off, so hopefully you can enjoy and maybe learn a thing or two from this. So I will go over the two iterations of this. My first being for a more smooth voxel planet, such as those found in games such as Space Engineers, and the second being for a much more high-res Minecraft style, but obviously with planets instead of flat terrain. I am using Unity 6.4 and I'm using Unity Dots, which is Unity's data-orientated tech stack, which comes with its own challenges and it does greatly affect how the project works, but in the long run it'll improve performance significantly, far more than I could probably ever achieve with typical mono behaviors. If you are unaware of how this works, that's okay, as currently it is not often seen outside some studios and indie devs due to its difficult learning curve, and by all means I am no expert using it, and information about it is fairly limited compared to the more traditional methods. So originally I was inspired to do this project by a popular YouTuber called Sebastian Larg, apologies if I didn't get your name right, where he made procedural worlds using marching cubes. I tried to replicate this somewhat and had some success, but it was far from perfect, but it at least got me working in the right direction for the future iterations of this project. So for the basics of how this works, I effectively generate a shit ton of noise, which I then form into a density field. You can think of this as a giant floating grid of values between -1 and 1, though admittedly this can depend on the implementation. For the exact specifics of how this terrain generation actually works, it's actually conceptually based on how Minecraft handles terrain, as is shown in a video by Henrik Gindenberg. Apologies if I didn't say your name right either. Which basically goes through all the steps that they take to combine all these noise maps into one to generate the shaping of the terrain. But with the obvious difference, at least for my implementation, being I'll take all this info and I'll still have to map it into a sphere, so I can then form a planet. This does come with a small drawback of how I've implemented it, that if I wanted to do a more like elliptical planet, or like body, it's not really doable due to how mine works. For how I actually hold this data, I store it all within a 3D texture, or at least I originally did, and then had my marching algorithm use it to then build the mesh that you would finally see as each of the chunks in game. Now I should state, for my generation in particular, I cannot say for other ones, I generate on a per chunk basis. I do not generate the entire planet's density field at once, as while it may be more intuitive, the issue comes to resolution, as it will then cause you to have an insane amount of data stored within this 3D texture, and if you want to have a decent resolution, while I could use interpolation to smooth it out, even this would not save a low resolution mesh. Now, if I was doing small or low poly planets, or even just generating asteroids, generating the entire body at once would be a reasonable approach, but as with anything, there is no shoe that fits all solution, and there may be better ones out there. So we now have our untextured planet that can't be edited in any way by the player. So for handling editing at least, I used a sparse octree implementation, which is actually already something that is often used in voxel games, such as Space Engineers, but by using this I won't exploit the player's memory, as much at least, which needs to be kept low in projects like this. As obviously the terrain is not everything in a game, and other systems will need it too. This is an issue that Space Engineers 1 at least ran into quite a lot, and caused your PC to sound like it's about to take off, due to the amount of memory that the game requires, amongst other things. To make matters worse, Players typically will either do a lot of edits to a chunk or very little, like digging out like a single dirt block, for example. And it means it's very hard to gauge how dense your data structure should be, which is why a sparse octree was a much better option for my project at least. This would also apply to saving chunks to the disk, as the process of saving every single voxel in a chunk that's had changes is a giant waste of disk space, and causes save files to inflate massively. So why save everything then, when I can just generate 90% of the voxel via procedural generation, and then load in the edits after? Now, onto the materials/textures. Currently, I have a very simple setup for handling textures, with me storing a voxel ID, which is an integer that represents dirt, stone, air as 0, 1, 2, so on, all the way up to 63, which I then pack into 6 bits, and then the density value into the remaining 10 bits of a single unsigned short, or a 16-bit integer. Hence why the IDs can only go up to 63, because anything larger than that would take up more than 6 bits. But you may be asking yourself, why? And it simply comes back to the usual problem being memory. And to make matters worse, as my generation is all done on the GPU via compute shaders, and with me using 3D textures, I need all my voxel data to be held in a single value for each place within the texture, otherwise I'm going to have to pass even more data through to the GPU, which has horrible overhead. So we now have the data for each of the voxels, but how would we then use this data with it only being used to generate a mesh? Well, it's pretty simple. We can pass the voxel IDs and their densities to each of the vertices within the mesh during the marching step. So now, when I get the vertex and the triangle data back, I can then store them within the UV channel, whilst I'm processing the mesh on the CPU side, which then becomes trivial to use and select a texture in a chunk shader to dictate what colour it should be. In conclusion, whilst this works okay, most of the time with decent performance, it is far from what I hope to achieve, and using mesh colliders for the chunks also murdered performance, and has caused me an immense amount of issues, which is why I actually wanted to take a step back and I worked on the new iteration with the grand return of a more cube-like approach, with a similar style to Minecraft, but at a far greater resolution. Now, for Minecraft-style terrain, typically you use meshes built from generated voxel data, via a process such as greedy meshing. Though other methods do exist, such as frame arching, which would work well here, and may be more performant, but it does come with its own challenges and trade-offs. But for my implementation, I chose to use greedy meshing, and unlike the Marching Cubes version, it doesn't require density values for the later stages, so they can just be used for the terrain shaping, and what each of the voxel IDs would be, which means less possible problems later on. Now for generation and applying the voxel edits, it more or less works the same to the Marching Cubes version, but when it comes to actually generating the mesh finally, the implementations diverge a lot. As greedy meshing, or at least in my implementation of greedy meshing, it is typically a very branch-heavy operation, which means basically that there's a lot of if statements required for it to function, and this is a general big no-no in compute shaders, and it makes the performance absolutely horrible. Now I will say there may be some implementation that would work with compute shaders, but I do not know how to implement one of those, to be honest. Fortunately, I can at least process the face masks on the GPU before handing them off to the CPU to generate the vertices and triangles for the mesh, which does at least make up somewhat for the performance and seems to run very well. And due to me generating the vertices again, I can store the voxel values inside of them. So texturing the voxels is almost identical to the Marching Cubes version, minus interpolation, as obviously we're generating cubes now. The other thing that my second iteration does differently is that I don't use mesh colliders, as they were difficult and expensive to create and update with the entities. So I made a custom physics implementation instead, because clearly that's easier, lol, which uses the voxel data to detect collisions, which allowed for far more responsive edits and less issues interacting with the voxels via raycasting, unlike with the Marching Cubes version. Unfortunately, there is not much to talk about it as it's incredibly basic currently. It doesn't really have many features outside of basic collision detection and handling dynamic bodies. Heck, the code itself is only about 300 lines long, and this is also including all the Unity dots boilerplate. Well, that is all for now. Thanks for watching. I hope you enjoyed and found that interesting enough, especially with me wanting to keep it fairly short, as videos like this do take a while to make. So like and subscribe if you learned something helpful, or just watching for fun. See you next time.